Welcome back to Arpit course on numerical methods in civil engineering, module number 4, lecture number 6, various finite difference schemes. So we have seen the finite difference formulation for as I mentioned the electric equations, parabolic equation and hyperbolic equations. So now large number of since so much development took place in the last century related to finite difference method as a numerical methods, and is one of the most commonly used method as a numerical technique. So that way lot of research work has been happened in the area of finite difference method. So here further we will discuss a few of the other schemes what is available in finite difference method. Of course, there are so much of other schemes are there, but we will be discussing few of the important schemes which especially we use in engineering or civil engineering specifically. So here in this lecture number 6 we are going to discuss the various schemes like explicit finite difference method schemes, diffusive scheme, upstream differencing, leapfrog scheme, 4-point formula, various implicit FDS scheme, Priceman scheme, ADI scheme, etc. So this is what we are going to discuss in this lecture. So like as I mentioned, there are so many finite difference schemes are available in literature. Some of the important schemes like diffusive scheme, upstream differencing scheme, leapfrog scheme, 4-point formula. This is what we are going to discuss. So as I mentioned earlier, so depending upon the scheme like explicit scheme or implicit scheme or Kronig-Nicolson scheme, the stability and the solution convergence depends upon which scheme you are using. So especially say for example, if you are using explicit scheme, even the solution may not converge. So that depends upon the problem and depends upon the time step or depends upon discretization. So, but most of the implicit scheme as we have already seen, that is converges and then it may take larger computation time, but definitely we will get a solution. So, that is the advantage of implicit scheme, and including Kronig-Nicolson scheme is also one type of implicit scheme. So, now first we will see a few of the explicit finite difference scheme initially, and then we will discuss the same few implicit schemes. So, as far as finite difference method is concerned. So, here first scheme which we would like to discuss is the diffusive scheme. So, here say for example, if this is the grid which we are considering, so this is the ij point which we consider. So, this is I plus 1j and this is I minus 1j and this is ij plus 1, I plus 1 j plus 1, I minus 1 j plus 1. So, this is delta x and this is the delta t, the time step. So, for example, if m is your variable and the derivative of m with respect to x and t, and the diffusive scheme we can write as del m by del x is equal to mi plus 1 j minus mi minus 1 j divided by 2 delta x. So, that means the value of m at this location, value of m at this location, that divided by 2 delta x. So, gives the derivative del m by del x. So, similarly, we can write the time derivative del m by del t is concerned. So, here you can see the del m by del t can be written as mi j plus 1 minus half of mi I plus 1 j plus mi mi minus 1 j divided by delta t. So, it is obvious. So, here we are finding the average of this with respect to this value and this value, and that is this value, and then it is the difference between mi j plus 1 to this difference divided by delta t. So, generally here we are discussing only the first derivative del m by del x or del m by del t, etc. So, now say del m by del y or second derivative del square m by del x square, del square m by del y square, all those things we can formulate. So, this when we write the final for the given equation, either a partial differential equation or ordinary differential equation, when we write like this, it is called a diffusive scheme. So, now another important scheme which we generally use is called upstream differencing scheme. So, here the same gridding as in previous. So, derivative of the non-variable m with respect to x and t can be written as del m by del x is equal to mi plus 1 j minus mi j. So, we are writing mi plus 1 j minus mi j divided by delta x. So, this is just like a forward difference scheme, and the or del m by del x is equal to mij minus mi minus 1j by delta x, which is backward, and then we write the time derivative del m by del t will be mij plus 1 minus mij by delta t as shown here. So, this when we write for the given equation either ordinary differential or partial differential equation by using these kinds of derivatives, it is called a upstream difference scheme. So, actually this is either forward or backward schemes which we directly apply. So, that kind of scheme when we develop in finite difference, it is called a upward differencing scheme. So, then another type of explicit scheme is called a leapfrog scheme. So, here we consider this ij, the point which we consider, then this is I plus 1 j, this is I minus 1 j, and here this is not j plus 1, but j only. So, this is I j plus 1, I plus 1 j plus 1, this is I minus 1 j plus 1. So, if you consider this, so del m with the first derivative del m by del x is equal to m I plus 1 j minus 1 m I, this is I minus 1 j minus 1 grid point. So, divide by 2 delta x. So, this is the first derivative of m, and time derivative we can write m I j plus 1 minus m I j minus 1, m I j plus 1 minus m I j minus 1 divided by 2 times delta t. So, this you can see we are using the central difference scheme, and then we approximate the first spatial or time derivative of m with respect to x, t or y or other derivatives we can write, and that is when we formulate the finite difference method like this is called a leapfrog scheme. So, we are taking to all corner points, then getting the derivative. So, I mean corner points means this with respect to this and with respect to this point and this point. We have discussed here the first derivative, but second derivative del square m by del x square or del square m by del y square or del square m by del t square also we can write in a very similar way. Then finally, another scheme is called 4-point formula. So, 4-point formula, actually you can see that here 4 points are there, this is I plus 1j, this is ij, and this is I plus 1 j plus 1, this is ij plus 1. 4 points are there with delta x and delta t. So, in this 4 points formula, del m by del x is taken as with respect to 1 by 2 delta x into mi plus 1 j plus mi plus 1 j plus 1 minus mij minus mi j plus 1 divided by 2 delta x. So, that is for the del m by del x, and del m by del t with respect to time we can write 1 by 2 delta t into mi plus 1 j plus 1 plus mi j plus 1 minus mi I plus 1 j minus mij. So, like this. So, when we formulate the given ordinary differential equation, partial differential equation with respect to this kind of formulation, so that is called a 4-point formula. So, as I mentioned earlier, there can be wide variety of finite difference schemes. So, various equations are formulated by combination of these schemes and depending on their needs, accuracy, stability, etc. So, for the given equation, either ordinary differential equation or partial differential equations, we can formulate taking. So, especially what we have discussed here is the explicit scheme. So, using these schemes we can formulate for the given equation, for example, Navier-Stokes equations or Saint-Venant's equation or any other type of equations, and we can formulate using the finite difference methods, especially the explicit schemes. So, now before going further discuss about the implicit scheme, we will see one especially Saint-Venant's equation. So, here an example problem, formulate the Saint-Venant's equation for one dimensional open channel flow using explicit diffusive finite difference scheme, and derive the expression for velocity of flow and depth of flow at point P. So, this is a explicit scheme. So, here this is the previous time step, this is the current time step which is where the unknowns are there. So, by using the values at these 3 points, we would like to get the values at point P. So, that is the unknowns at unknowns here are velocity and depth of flow, and that is what we need to get at this location. So, here the governing equations as I mentioned, these are the Saint-Venant's equations for open channel flow. The continuity equation we can write A into del V by del x plus V into del A by del x plus T into del Y by del T is equal to 0. So, here small t is the time step, capital T is the top width of the channel, A is the area cross section, I mean the vector area cross section, flow cross section, V is the velocity, and x is the spatial say in one dimension. This equation is in one dimension. So, now very similar way we are having the momentum equation. So, here del y by del x plus v by g del v by del x plus 1 by g del v by del t is equal to S0 minus SF. So, here y is the flow depth. So, here S0 is the bed slope and SF is the energy slope, V is the average flow velocity, A is the area cross section of the channel, T is the top width of the channel. So, here say for example, this is the canal or the stream which we are trying to approximate. So, we can use this continuity equation and momentum equation to find out the velocity. I mean from the given boundary conditions we can get the velocity and the depth of flow at a particular location. So, by using the final difference method. So, here we are going to formulate these using the explicit final difference scheme. So, that is explicit diffusive final difference scheme we are going to formulate. So, now here we have already seen the diffusive scheme. So, by using the diffusive scheme, the values of V and Y are known at R and S. So, this is our discretization. So, this is the time step, previous time step, this is the current time step. So, using these values, the velocities and the depth of flow at R and S, we would like to find the velocity at this location. So, our discretization delta x in x direction and delta t in the y direction. So, as we have already seen the explicit diffusive scheme, so del y by del x we can write say with respect to this figure ys minus yr divided by 2 delta x, and del v by del x can be written as vs minus vr by 2 delta x. So, similarly, del y by del t we can write with respect to this. So, here the unknown yp comes. So, yp is this location yp minus half of ys plus yr by delta t, and del v by del t can be written as vp minus half of vs plus vr by delta t. So, that is del y by del t, del v by del t, and we have already written del y by del x and del v by del x. So, now using all these derivatives we can write the equation. So, now here please note that this SF is the energy slope. So, here say for example, if this R and S 2 points are there. So, generally in this kinds of numerical approximation we take the average of this. So, SF is equal to half of SFS plus FSFR. So, that is what is written. And now for a for a rectangular cross section, so for area is equal to T into Y. So, area A for a rectangular cross section T into Y. So, this we can write the equation. Now, the actual equation we have already seen here. So, this is our actual equation which we are trying to solve, the continuity equation and the moment equation. So, equation number 2. So, if you take the continuity equation, so then we can write say with respect to this figure yr plus ys by 2 into t into vs minus vr by 2 delta x plus vs plus vr by 2 into t into ys minus yr by 2 delta x plus t into yp minus half ys plus yr by delta t, that is equal to 0. So, this is for the continuity equation. So, very similar way for the momentum equation in one dimension we can write ys minus yr by 2 delta x plus vs plus vr by 2g into vs minus vr by 2 delta x plus 1 by g into vp minus half vs plus vr by delta t is equal to S0 minus half of SFR at this location. So, now this is an explicit scheme. So, what we are doing? So, with respect to these values, known values, we are finding the unknown at this location, especially the velocity and the depth of flow. Solution is directly we get solving for velocity and depth of flow at point P. With respect to this figure, we can write Vp is equal to Vs by Vr by 2 plus half of delta t by delta x into half Vr square minus Vs square plus g into Yr minus Ys plus g into delta t into S0 minus half SFS plus SFR So this is what will be finally, if you solve those equations, you get it explicitly Vp, and Yp will be equal to half Yr plus Ys into plus delta T by delta x into Qr minus Qs by Tr plus Ts. So with respect to this figure. So here where Tr, here if Tr is equal to Ts, Qr is equal to A into Vr and Q is equal to A into Vs. So this is, as you can see, this is the explicit scheme. So advantage is that we are already from the known value, we are explicitly finding the unknown value. So here in this case, unknown is at this location P. From the known value of at a velocity and depth of flight R and S, we are finding the unknowns at P, the velocity and depth of flight. So that is about the example problem. So now we will further discuss the implicit finite difference scheme. So we have already seen the explicit finite difference scheme are stable only when the following conditions are satisfied. Actually, the space discretization time and the time discretization should be small to get a satisfactory solution using the explicit scheme. We can have a condition called a Courant number. So here if say for example, u is the velocity of the flow, u delta t by delta x should be less than or equal to 1, where u is the average velocity, and if c is the wave celerity, we can write c plus u into delta t by delta x should be also less than or equal to 1. So, well, wave celerity means c is equal to square root of g y, where y is the depth of flow and g is the acceleration due to gravity. So, this condition generally we need to satisfy the as far as time step and spatial discretization is concerned. So, this is a given condition, otherwise the solution will not be stable, the solution will diverge. So, that is the problem with the explicit scheme. But implicit schemes are generally stable and consistent. So, that is the advantages of implicit scheme. So, stability. So, here as you can see, stability means solution converges without say any divergence. I mean the solution will be the error will be keep on decreasing, and finally we will have a converged solution. Say for example, if this is a figure which you can see here. So, if this is the error, so error will be keep on decreasing like this, and then it will be converge. So, now at this location this is a number of iterations. So, this is function value which we consider. So, like u or whatever it is. So, it will be decreasing and then it will be converging. But explicit scheme, if the high time step is a large time step is there, it will not converge, the solution will not be stable. So, that is the problem with the explicit scheme. And then also in explicit scheme there can be some overshooting like this also. Sometimes instead of getting a smooth solution, we can have a overshooting or undershooting. So, that also possible. So, now but in implicit scheme generally the scheme will be stable. So, that is the advantage. Then another important aspect is the consistency, whether the finite difference scheme is said to be consistent if the finite difference form of the equation tends to the original difference equation as delta x and delta t tends to 0. So, so this is consistency also important. The finite difference scheme is said to be consistent. So, if the finite difference of form of the equations tends to, I mean depending upon delta x and delta y or delta t, so that tends to 0, the equation to original equation is obtained. So, then we say the system is consistent. So, when we deal with the numerical solution, we need to see that whether the scheme which we are using is stable, consistent, and then there is numerical overshooting or undershooting, that kind of issues we need to see. Generally explicit scheme that kind of problems are there, but if you keep it within the Courant number criteria, all those are met, then we will be getting a better solution, or especially the time step is small. But then many times if say for example, for large scale problems like aquifer problems, we need to say go for simulation for so many years, say 10 years, 20 years or 100 years like that, then using small time step is very difficult. So, that is why implicit schemes are important. So, there are so many implicit schemes, various implicit finite difference schemes are available in literature. Two of the commonly used scheme is called, one is called a Preissmann scheme, second one is called a alternative direction implicit scheme, ADI scheme. So, we will briefly discuss. So, there are so many schemes are there, but we will discuss 2 important schemes only. Due to lack of time, we will be discussing only 2 schemes. So, in the Preissman scheme, so you can see with respect to this typical grid shown here. So, this del u by del t can be written as u I j plus 1 plus u I plus 1 j plus 1 minus u I j plus u I plus 1 j divided by 2 delta t, and del u by del x, especially with respect to space, we will be using a parameter alpha, which is the multiplying coefficient alpha into u I plus 1 j plus 1 minus u I j plus 1 divided by delta x plus 1 minus alpha into u I plus 1 j minus u I j by delta x. So, here u is equal to half u alpha half alpha into u I plus 1 j plus 1 plus u I j plus 1 plus half 1 minus alpha into u I plus 1 j plus u I j. So, this is j jth level, j plus 1th level. So, this is I minus 1, I plus 1. So, we are using the Preissman scheme, we will be using this approximation. So, depending upon the problem, whether it is first order, second order, we can rewrite the scheme. So, here alpha is a coefficient, alpha is generally used to put 0.6 to 0.7. If alpha is equal to 0, this Preissman scheme will be explicit scheme, totally explicit scheme, and if alpha is equal to 1, it is a totally implicit scheme. Generally, it is observed when alpha is between 0.5 to 1, it will be the scheme is stable. So, that is called a Preissman implicit scheme. So, that is one of the commonly used final difference scheme, Preissman scheme. So, now we will discuss the another commonly used scheme, implicit scheme, alternative direction implicit scheme, ADI scheme. So, here let us consider this equation del square h by del t x square plus del square h by del y square is equal to s by t del h by del t. So, this is the diffusion equation 2D, 2 dimensions. So, here we demonstrate this ADI scheme by taking a typical example like this. So, these are actually this is a say a Dirichlet boundary value problem. So, here all these boundary values are known, we would like to get the unknowns at this 4 locations. So, this is x, y and then time is t. So, here S is in this equation, this is actually the groundwater flow equation, especially for confined aquifer problems. So, S is the Story coefficient, T is the transmissivity and H is the hydraulic head. So, this is now we let us take the same delta, the special discrimination, let us assume delta x equal delta y is equal to A, or which is sometimes put it as Q for clarity. So, here n represents the time, time level is represented by n, and this is a 2-dimensional problem and time is also involved. So, the space discretization is A or Q, and that is delta x equal to delta y. So, now so using the fully implicit final difference scheme for equation 1, so here we can write h I plus 1 j n plus 1 plus h I minus 1 j n plus 1 h I j plus 1 n plus 1 plus h I j minus 1 n plus 1 minus 4 h I j n plus 1 is equal to s q square by t into h I j n plus 1 minus h I j n by delta t. So, please note that the q is equal to a is the space delta x equal to delta y, and n indicate the time, I indicate the x direction, j indicate the y direction. So, this is a 2D problem. So, rearranging the terms to put unknown terms to on the left hand side and known terms on the right hand side, we can write h I plus 1 j n plus 1 plus h I minus 1 j n plus 1 plus h I j plus 1 n plus 1 plus h I j minus 1 n plus 1 plus minus 4 minus s q square by t delta t, the h I j n plus 1 is equal to minus s q square by t delta t h I j n. So, by putting the known values to the left, right and unknown values to the left. So, please remember q is equal to a is the space delta x equal to delta y. So, now the alternative direction implicit scheme, according to this figure, we want to identify what are the unknowns here, these 4 locations. So, the resulting system can be written in matrix form like this. So, minus 4 minus s q square t delta t 1 1 0. So, here our 4 unknowns are there. So, that is why 4 by 4 matrix. So, this is 1 minus 4 s q square by t delta t. Please remember q is delta x or delta y, that 0 1 and 1 0 minus 4 minus s q square by t delta t 1 and 0 1 1 minus 4 minus s q square by t delta t, and here our unknowns are S22 n plus 1, n plus 1 is the current time step, S22 S32 n plus 1, H23 n plus 1 and S33 n plus 1. These are the 4 unknowns, and that is written in terms of the previous calculated values or known values. Please remember this H21 is a H12 are known values. So, these are all the known values either given as boundary conditions or from the previous time. So, we can reformulate this as a matrix form. So, in ADI alternative direction implicit scheme, the tridiagonal coefficient matrix is to be obtained by writing this. So, this is not a tridiagonal. So, generally tridiagonal means which is easy to solve, and we can solve a very large problem. So, that is why we are making a tridiagonal coefficient matrix to obtain by writing the final difference equation firstly implicitly along the column. So, this is along the column we write first, and then explicitly along rows, and then vice versa. So, that is the scheme alternate direction implicit scheme. So, actually firstly implicitly along column and explicitly along row, and then vice versa. That is why it is called a ADI scheme. So, here in along columns are approximate time n plus 1, and h along rows are approximate as time n. So, we can rewrite the equation as in equation number 5. So, here you can see h I j n plus 1 plus minus 4 minus s I square t delta t, h I j n plus 1 plus h I j plus 1 n plus 1 is equal to minus s q square by t delta t, h I j n minus h I minus 1 j minus h I plus 1 j n. So, this is equation number 5. So, equation 5 yields a triangular coefficient matrix along any column. The explicit approximation along rows uncouples one column from another. So, that is the advantage of the ADI scheme. So, now if you write for the second column, so this is the second column, we can write S22 n plus 1, S23 n plus 1. So, this first column, second column. So, here we can write the equation in this form, equation number 6. So, these are all the known values. So, we write like this. And similarly, for third column also we can write. So, here so S32 S33. So, first S22 S23 and then S32 S33. So, this is for the second column. So, we can write as in equation, I mean here in this case please remember this is first, this is second, this is third. So, that is why second column, and this is the third column. So, we can write the equation as in equation number 7. So, now combining equation 6 and 7. So, please remember our space delta x equal delta y is equal to q is equal to a is mentioned here. So, we can rewrite this equation in the form of equation number 8. So, please remember 2 2 3 2 3 3 2 3 3. So, these are the 4 unknowns we can rewrite. So, these values are all known values from the boundary conditions, and these are the S32 is from the previous iteration we are getting it, and these are all the known values we can write in the form of equation number 8. So, similarly, we can write implicit along rows and explicit along columns, and finally, this equation h I minus 1 j n plus 1 plus minus 4 s I square t delta t h I j n plus 1 plus h I plus 1 j n plus 1 is equal to minus s I square t delta t h I j n minus h I j n minus h I j plus n. So, like that we can write. So, that way as you can see in the ADI scheme what we are doing. So, we write, so we are transforming the main concept behind ADI scheme is that so here the tridiagonal. So, we want to get a tridiagonal coefficient matrix, which is here initially it is not tridiagonal. So, we are transforming this into a tridiagonal coefficient matrix by firstly doing it along the columns as implicit and then explicit and vice versa. So, that is the basic principle. So, that operation is done here in this equation 6, 7 and 8, and then we write similarly we can write along the rows and explicitly along columns, like that we can continue. So, that is about the implicit scheme. So, what we have discussed so far in this lecture is the various kinds of explicit schemes and implicit schemes. So, as far as finite difference method is concerned, so we took specific equations as far as the formulation is concerned, but we can write this equation for any kind of I mean we can formulate the finite difference scheme for any kind of equation, either ordinary differential equation or partial differential equations. So, that is about the lecture number 6 in module number 4, and we are here also we are having an assignment, number 6 as far as this lecture is concerned. We will briefly discuss. So, here we are discussing about the say module number 4, say lecture number 6, assignment number 6. So, here only one problem is there: formulate the water hammer equation using the explicit diffusive scheme and derive the expression for head or pressure and velocity at the point P, assuming so velocity or the say flow rate. So, here Q is equal to AV, you can substitute and achieve the pressure, assuming the values at the point R and S are known. So, here water hammer equation, continuity equation is in water hammer, we are having the continuity equation, moment equation. So, here del Q by del T plus dA into del H by del X plus F by 2 dA, Q modulus Q is equal to 0. And so, this is the dynamic equation, and then continuity equation S square into S square Q by del X square plus dA into del H by del T. H is the head or the pressure, and T is the time, Q is equal to A into V the flow rate, and A is the area cross section, G is the acceleration due to gravity. So, this especially water hammer equation is used in pipe flows, and F is the Darcy-Weisbach friction factor, D is the diameter of the pipe. So, and A is the water hammer velocity. So, this equation as we already seen earlier, the explicit diffusive scheme, you can use it to say, for example, if you assume that this location values are known, you can explicitly find the pressure or the head, H in this case H, head at this location, and also the velocity or the flow rate can be found by using the explicit scheme. So, this is about the assignment number 6. Lecture number 6 in module number 4. So, that is about lecture number 6 in module number 4. So, we have now discussed so far various final difference scheme. So, we will be further discussing one more lecture in final difference method, especially how to deal with the field problems. We will be discussing the next lecture. Thank you very much.